This is a video on graphing functions that can be rational functions, but also can have similar attributes of rational functions, but when you're not expected to find the x-intercepts. Either it's going to take too long to do so, or you actually algebraically can't. Okay, so let's do this first one here. So here's the first problem. And again, I would say don't find, or you can't find the x-intercepts. It doesn't mean there isn't any, but we just aren't going to find the exact x-intercepts. We're going to have to use the rest of the data to kind of figure out where they might be to get a rough sketch of the graph. All right, so one thing that I noticed is it's a square root function, which definitely limits the domain. So it's going to have a finite starting point. So that will be, because the domain is limited, just thinking about the square root to anything where the square root is 0 or above. So I need x to be greater than or equal to -4. So my leftmost point is going to be x coordinate of -4. And then if we plug that into this function, the y coordinate would be 0 minus 2 over -7. So -4 2/7 is that kind of leftmost point. All right, some other things we can find is, let's see if there's a y-intercept. When I plug in 0 for x, I'm going to get 2 from the square root piece, minus 2 over -3, so 2 2/3. It's my y-intercept. There's a vertical asymptote. There's a denominator here in vertical asymptote, which creating that explosive behavior, whereas the denominator is 0. So x equals 3. EBA, there is an EBA here. So as x gets huge, let's look at what's happening here. As x gets huge, this piece will be going towards 0 because it's bottom heavy. So I'll just be left with it going towards infinity, but along what's left over of the graph, the function, square root of x plus 4. So that's my EBA. So my EBA is y, whoops, don't want to use the, oops. Let's see if I can erase this. There we go. So my EBA is y equals the square root of x plus 4. And let's see if it crosses EBA. Remember how to do that? You set the function equal to the EBA and see if they intersect. And because it's in the function itself is in that nice form, it's easy to see if it crosses the EBA. And it would cross if -2 over x minus 3 equals 0, which it doesn't. That's impossible. So no cross. All right, and so unfortunately, the downside of not having x-intercepts means we can't do proper sign analysis. Because remember what we put on our sign chart, because a graph could change sign, meaning go from the y values could go from positive to negative or negative to positive at x-intercepts or vertical asymptotes. But I don't know what the x-intercepts are, so I can't do that. But there is something else we can do, which is another strategy, which is let's see if we can discern when the graph is above or below the EBA. And to do that, we're going to pay attention to what our EBA is. So our EBA is this piece. So let's pay attention to the other piece, and let's look at where it changes sign. Because in this case, it makes it a little harder because it's a minus. If my graph, the y values of my graph, if I'm subtracting positive values from the EBA, then I'm going to be below the EBA. If I'm subtracting negative y values, then I'm going to be above the EBA. I'll show you what I mean in a minute. So this extra piece, let's see where it changes sign. It changes sign where the numerator is 0, which is never, and where this denominator is 0. And there's only one place for that. So I'm only going to be putting 3 on this chart. And again, it's not sign chart in terms of above or below the x-axis. It's a sign chart in terms of above or below the EBA. So if I plug in values greater than 3, say I plug in something like 4, then this piece here, okay, so if I plug in something like 4, then I've got this piece, again, the piece I've highlighted, would be 2 over 4 minus 3, which is a positive value. So think about when I plug in 4 to the function. I would plug it into the square root, so you'd get square root of 8. So the y value of the EBA, I'm going to do it this way. Let's think about the y value of the EBA, and this is at x equals 4. And let's think versus y value of the function. The y value of the EBA at x equals 4 will be root 8. But the y value of the function will be that y value of the EBA minus what we just said, 2 over 4 minus 3, which is a positive number, and it's just 2. So notice for values greater than 3, you're going to be subtracting positive from the EBA y values. So it means that all the y values of the function when I'm greater than or 3 are going to be below the EBA. Whereas if I put in something less than 3, like 2, that's going to make this quantity here negative. So I'll be subtracting a negative from the y value of the EBA in order to get the y values of the function. So the function itself would be above the EBA. And this is going to be valuable information to know for our graph, especially because we don't have those x-intercepts. And that's why I'm doing that above the EBA. Okay, so now let's go to our graph and let's put down what we've got. So I've got the leftmost value of -4. And actually, before I do that, let's graph this EBA. Let's put our EBA, all our dotted things on first, our vertical asymptote and our EBA. So the vertical asymptote, to graph y equals square root of x plus 4, it's the square root function, which is slow growth, shifted to the left 4. And it's important to know, especially in this problem, where it hits the y-axis. Always good with your EBAs to know where they hit the x and y-axis if they do. So it's going to look like this. Got my slow growth there. And then my vertical asymptote at x equals 3. And now let's put on some points we know. We know that the y-intercept is 2 2/3. So notice it's going to be above that EBA. And the leftmost point is -427. So again, just above the EBA. And so let's now go to this chart we created. To the left of 3, I'm always above the EBA. So that means if I'm always above the EBA, to the left of the vertical asymptote, I must be going towards infinity. And then it's going to be going through these points. And we know it doesn't cross the EBA. All right, and now on the other side of the vertical asymptote, we're below the EBA. So I can't be going towards infinity. Instead, I've got to be going towards negative infinity. And then I'm going to get close to the EBA. So there's definitely an x-intercept somewhere. I don't know exactly where it is. So that's how you would do that. Okay, let's do another one. All right, let me make some room here. Okay, here's my second one. Let's do y equals x squared minus 1 plus 2x plus 1 over x squared. Again, I would say in the directions, no need to find the x-intercepts here, or you can't find them. In this case, let's start with, there's no square root, so I don't have to think of like a leftmost or rightmost point. There is no y-intercept, because if I plug in 0 for x, in the second part of this function, I'd be dividing by 0, so that's a no-go. There is a vertical asymptote, x equals 0, and I'm noting I'm looking and seeing it's squared, so it shouldn't be changing side across that vertical asymptote. The EBA is as x gets huge, this part here will be going towards 0 because it is bottom heavy. So my graph will be getting positively huge, but in fact, when I put them both positive and negative infinity, it'll be getting positively huge. But along the path of the graph x squared minus 1. So that's my EBA. So y equals x squared minus 1. Then I want to figure out, is it crossing the EBA? So remember, set the function equal to the EBA. And again, in this form, it's kind of nice because that will cancel when I'm solving to see if it crosses. And it only crosses if this piece equals 0. And an only way a fraction equals 0 is the numerator equals 0. So it'll cross at -1/2. So yes, at -1/2. How do I find the y coordinate of that cross? Well, I think it's always easiest just to plug it back into the EBA because it's the cross of the EBA and the function. And the EBA is much simpler here than plugging into the whole function. So when I plug it into x squared minus 1, I get a 4th minus 1 or -3/4. So always nice to have another point on the graph. Okay. Again, we can't do sign analysis as we know it because we don't know the x-intercepts, but I can do a bit of sign analysis with this piece. So the numerator is 0 at -1/2, the denominator is 0 at 0. So this piece, if I plug in greater than 0, we're going to be positive. So I'm going to be adding to the EBA, so I should be above the EBA. And on the other side of 0, I'm still positive for this piece, so I'm still going to be above the EBA. But then when I go across -1/2, like plug in something like -1, that piece is going to be negative, so I'm going to be below the EBA. Again, this is important pieces of information to help my graph. Okay, so again, nice to do the dotted line things first, like the asymptotes. So x squared minus 1 is the EBA, and then x equals 0. It's a vertical asymptote. Maybe I should have done the asymptotes in different color than the axes, but okay, so, oh, and let's do the other point. Oh, Lord, I wish I had done this a little bigger. So the point it crosses the EBA is -1/2, -3/4. So we'll put it there. Okay, I think, when you're confused about what a graph looks like, go to the vertical asymptotes. So the vertical asymptote, there's only one at x equals 0. To the right of it, I'm above the EBA. So I've got to be going towards infinity then. And then I know it's definitely not crossing to the right of 0. We found where it was crossing, so it's got to look something like this. Do I know how low it goes? I do not. But I do know it has to eventually come back towards that EBA. And notice on the other side of 0, I'm still above the EBA, so I'm still going towards infinity. But then I'm going to cross the EBA at that -1/2, -3/4. And then I'm going to be below the EBA. But remember, you still have to, at the ends, go towards the EBA, which is going to be towards infinity in this case, just like the EBA. So that's your graph.